好，大家好啊。Welcome to NCTS 5053, Differential Forms in Algebraic Topology. This course will be taught in English, partly because I don't know how to say many of the terms in Chinese, but also because the university thinks that it's good for you to get some practice in English. Okay? However, you can ask questions in English, in 国语, or 台语嘛会使。我先用国语自我介绍。我叫杜武亮，我出生在台北，不过在高雄长大。初中的时候移民去加拿大，后来搬去美国，在加拿大和美国念中学、大学和研究院。那我现在是 Boston 附近 Tufts 大学的教授。Okay, now I will switch back to English. You know, the textbook for this course is Differential Forms in Algebraic Topology that I wrote with my professor at Harvard, Raoul Bott, more than 40 years ago. Okay. Another book that you would find useful is my book, Introduction to Manifolds. Now, I will put both books on the course website so that you don't have to buy them. But I'm still trying to figure out how to set up this course website. But, you know, I should be up and running before the next class, okay? Okay, now, I would like to know something about your background. So how many of you have studied differential forms or manifolds? Can you raise your hand? Okay, many, but not everyone. Okay, well, that's okay. You know, I'm going to start with a review of differential forms. But if you have not studied before, you know, I have written up a kind of short summary of about, I think, 20 pages on manifolds in differential forms, and you can read that, and it will be on the course website, okay? All right. Okay, so today I'm gonna talk about the Rham complex on Rn. Okay. And the first question I want to answer is, what is dx? Okay. Because in calculus, you write dx all the time, you know, the integral of f dx or df dx. But what does it mean, you know? And in calculus, you may have been told that it's just a notation, or maybe it's an infinitesimal, or maybe it's an approximation, you know, a short quantity when x varies, okay? But it actually has a precise meaning, and it is a differential forms, and so that's what I want to explain. Okay, so let's start with this example of the determinant of 3 vectors in R3, okay? So for ABC in R3, the determinant of the matrix ABC is a number. Now, it has the property that it is three linear, and that means it's linear in each of the three variables, A, B, and C, separately. Okay? And in addition, it's, well, what happens if you switch two columns? Let me see. What happens to determine when you switch two columns? Yeah, you get a minus sign. Okay, so whenever you switch two columns, you get a minus sign. And this property is called alternating. Okay, so we'll generalize that. Okay. We can consider a function of k arguments, which is linear in each argument, and that's called a k-tensor. So a k-tensor on a vector space V, it's just a k-linear function. And a k-tensor is alternating if whenever you switch two arguments, you get a minus sign. So, I'm going to call a k-tensor alpha. Okay? So a k-tensor alpha is alternating if, well, actually, a permutation is a composition of transpositions. So more generally, we can say that for a permutation of the numbers from 1 to k, whenever you apply a permutation, you pick up a sign. So, okay. Sk is the set of permutations of 1 through k, and alpha is alternating if whenever you permute the arguments, by sigma, then you get a sign of sigma times alpha times V1 to Vk. Okay? So that's an alternating k-tensor, and the determinant is an alternating 3-tensor. And then I will use this notation, ak of V. Oh, this moves. I didn't know that. That's great. Yeah. Okay, ak of V is the set of all alternating k-tensors on V. Okay, yeah. All right. Okay, so let's now look at K forms here. Okay, so maybe I'll write here. Now, you know, Rn is a vector space, but you also can consider it as like a geometric object, you know, like R2 is a plane. And so at each point, you know, you have tangent vectors, and you can talk about the tangent space, okay? So in this lecture, U will always be an open subset of Rn. And P is a point in U. Okay. And I'm gonna write P a point, you know, with parentheses. And these are the coordinates of the points, P1 to Pn, okay? Now at P, you can have a vector, okay? So V, but I write a vector as a column, V1 to Vn, or horizontally with angular brackets. And that's called a tangent vector at P, okay? And so the notation for the tangent space at U, tangent space at P of U, okay? So that would be the set of all vectors V1 to Vn, like this, where Vi is in R, okay? Well, so you see that the tangent space is given by n numbers, just like a point, okay? So it's isomorphic to n. But I want to make the distinction between the tangent space and points in Rn. Okay? Now, in Rn, you have a standard basis. E1, E2. Mm-hmm. And if these are vectors at P, then I will put a subscript there. So E1P is the vector 1, 0, 0, dot, dot, dot. And E2P is the vector 0, 1, 0. Okay? And so a tangent vector, you know, if it's V1 to Vn, then it's just a sum of Vi, Ei at P. Okay. Right? Okay. Okay, now what is a differential form? So a K form on U is it's an assignment of a k-tensor, alternating k-tensor to each point, okay? So at each point, you have an alternating k-tensor omega p is an assignment to each p in U of an alternating k-tensor omega p on the tangent space. Actually, before I define a differential form, I really should ask you, like, what is a vector field? What is a vector field on U? How do you picture a vector field on U? What's a vector field? A vector is an arrow, right? And what's a vector field? Well, a vector field is something like this, right? I mean, this is a vector field. So how would you define a vector field? Yes? Couldn't hear you. You need a microphone. Yeah. Oh, there is a microphone here.
Point a tangent vector.
Yeah. So it's an assignment of a tangent vector to each point, okay? So, yeah, to each point, you assign a tangent vector, xp. Okay? So a differential form is just like a vector field, except instead of assigning a tangent vector to each point, you assign an alternating k-tensor. Okay? Yeah, so that's a definition. But like more precisely, a k-form omega, a k-form is a function omega, okay, whose domain is U, because to each point in U, you assign something, and whose target space is the union of the alternating k-tensors on U. No, the alternating k-tensors on each tangent space to U, right? Yeah. And P varies over all points of U. Okay, so a differential form assigned to each point P in U and alternating k-tensor on the tangent space. So that means you also have to require that omega P is in AK of TPU. Okay, so that's what the differential form is. I think, this one goes up and this one goes down. Okay, well, let's look at some examples of differential forms. Let me see. So one way to get a differential form is to take the differential of a function. Mhm. So. Okay. Okay, so I'm going to use this notation. C infinity U is the set of C infinity functions from U to R. Mhm. And yes, and if I have a C infinity function, on U, I define, okay, df to be the one form such that, okay, for all P in U, now df at P, that should be an alternating one tensor on the tangent space. Okay? Well, if you have only one argument, there's no way to permute this, so an alternating one tensor is the same as a one tensor. Okay? So df at P should take a vector to a number. Okay? So you have df at P of V now, if you just think about this, I mean, yeah, if you have a function, a point, and a tangent vector, given these three pieces of data, how do you get a number out of it? Like if you have a vector and a function, a vector and a point and a function, okay? So, so here you have a point P, you have a vector V, and you have a function. You have some function. There's only one way to get a number out of this data. What is it? How do you get when you have a vector at a point and a function, how do you get a number out of that? Yeah, you just take the directional derivative, okay? So this should just be the directional derivative of f in the direction v. Directional derivative. Yeah. That's the only possible definition that you can make. You know, but I'm going to just introduce a simpler notation. So instead of writing dVF, just write VF. Yeah. See? It saves you some work. So VF just means the directional derivative. Okay? And yeah, and this is a one form. Okay? So that's what dF is. Okay? And since X is a function on R3, that's what dx is. Okay, dx is a one form. on R3. But I think, let's see, from calculus, do you remember the formula for the directional derivative? Like, so if you have a function f and you have a vector v at p, how do you calculate the directional derivative? Like from calculus. V, so if V is the sum of VI, EI at P, then, no, gosh, I'm still trying to figure out how to work these blackboards. Then there's a formula for the directional derivative. Then VF, that's dVF is equal to, yeah. So anyone, what's the formula for the directional derivative in terms of the components of the vector? Yeah, that's from multivariable calculus. Yeah, right. So the inner product of the gradient of f, so the gradient is the partial derivative. And then you take the inner product with v, so this is the formula. Vi, dxip, sum over all I, okay? Now, on the other hand, this V is the sum of VI, EIP, and you apply it to F. Okay? And here, like I can write this as the sum of VI, VDXI evaluated at P applied to F. And if you compare these two formulas, well, you see that the formula tells you that you simply replace this by this. And so I'm going to introduce a new notation. Okay? Instead of writing EI at P, I'll write that. See, you make this identification. What is the advantage of this? Well, the advantage is that once you introduce this notation, you don't have to think. You don't have to remember any formula, because to calculate VF, well, the notation already tells you what to do. Yeah. So in the future, instead of writing EIP, I will just write DDXI, evaluated at P. Yeah, so I'm going to treat this partial derivative as a tangent vector. Okay? We make this identification. Okay, and so now let's let's work out. Let's just see what dxi means. Okay. Okay. So okay. Now dxi, we said it's a one form. So at each point P, it's a one tensor on the tangent space. No, just a minute. It's a one tensor. Sorry, yeah, it's yeah. dxi is a one tensor. No, just a minute. Sorry. Now the definition of dxi. Oh, right. Yeah. It's a one tensor. Yes. So it's gonna take a tangent vector to R. And so let's apply it to a tangent vector. And by the definition of the differential, this is just the directional derivative applied to the function xi. So this is the definition of the differential. Okay? And V is the sum of, now instead of using I, because I have to use a different letter because I is busy. So it's the sum of Vj, EJP applied to Xi. But as I said, we are going to identify EJP with DDXJ at P. And when you differentiate Xi with respect to Xj, you just get 1 or 0. And that is the Kronecker delta. Do you all know this symbol, the Kronecker delta? Who doesn't know this symbol? Don't be shy, raise your hand. Yeah. Okay, you all know it, right? It's either 1 or 0. And it's 0 if I is different from J, and so all the terms vanish except for the ith one, VI, okay? And so what you see is that dxi, it's the one form that picks out the ith coordinate. Okay? So that is what dxi means. Yeah, I see that I should do this. Yeah. Oh. So let's write down our discovery. Yeah. dxi is the one form on U that picks out the ith coordinate, the ith component of a tangent vector V at P. Okay, so that's what dxi is. And now if somebody asks you, what is dx on R3? Dx is the one form that picks out the x coordinate. Okay? So that is the proper answer if anybody asks you what dx is. Okay, okay. Now, the class goes from 10:20 to 11:10, right? Yeah, so we still have a few minutes. Okay, so differential forms can be added and multiplied. It's obvious how to add them because you are just adding two functions. Okay? But multiplication is a little bit more complicated. And it's called the wedge product. So okay. And here's the definition. If alpha is an alternating K-tensor on a vector space V, and beta is an alternating L-tensor on a vector space V, then alpha wedge beta is an alternating K plus L tensor on V, and it's defined by. Now, since it's an alternating K plus L tensor, it needs K plus L arguments. Okay, and the definition is not that obvious. So what you do is you apply alpha to any K of these arguments. Okay? So you can, that means you permute, you permute them and you pick out K of them. And then you apply beta to the rest. And there's a sign, which is the sign of the permutation, and sigma permutes all the integers from 1 to K plus L. Oh, yeah, and then there's going to be a lot of repetitions, so you have to divide by K factorial, L factorial. Okay? That is the definition. Well, so like, let's look at an example. If you start with 1 tensors, then alpha wedge beta is a 2 tensor, so it has 2 arguments. And So you take alpha, and then there are only two permutations of 1 and 2, the identity, B1, that comes with a plus sign, and then the other one is you permute B1 and V2, that comes with a minus sign, okay? So you get this formula for the wedge product of 1 tensors. And you are just dividing by 1 factorial, 1 factorial. Okay? Doesn't matter too much what the formula for the wedge product is, because all you care about here is that it has that the tensors can be multiplied. Okay? The alternating tensor can be multiplied. And then you can do this at every point, right? To get the wedge product of a K form and an L form. Okay? So so definition, if alpha is a K form and beta is an L form on U, then alpha wedge beta at each point, it's just defined to be alpha P wedge beta P. And these are alternating K tensors at each point, okay? So for all. Okay, yeah. All right, and then, now, it's very important that we have a local expression for differential forms. So let's see. Yeah. Okay. Differential forms in terms of coordinates. Okay, now, my first proposition is that dxi, oh yeah, so dxi applied to dd. Okay, no, my first proposition is that dx1 to dxn is a basis for the dual space, okay? Now, if V is a vector space, then the dual space is written this. And do you know what the dual space is of a vector space? Yeah. Okay, tell me what the dual space is. Did you nod your head? Yeah, so it's all the linear functions f from the vector space to R. So it's actually a one tensor. Yeah. Because a one tensor is a linear function from V to R, and it's also the alternating one tensors because there's nothing to alternate. Okay, and yeah. Okay. Oh, I'm getting a lot of exercise here, just pushing the blackboards up and down. All right, so the proposition is that dx1 to dxn, okay, is the dual basis for TPU dual to ddx1 at P to ddxn at P. And I should put P here. Okay? Yeah. And this is easy to check because, oh, I think we did it already, right? Because dxi applied to ddxj is delta ij. Okay, so that means it's a dual basis. And therefore, every one form omega on U can be written as omega. Okay, you can write it in terms of the basis, dxi, with coefficients ai. Okay? Now, it's really at each point, right? But you can drop the p. So you just write omega is the sum of ai dxi. Okay? And then where ai is now a function because it depends on p, where ai goes from U to R. It's a function. Okay. You can write every one form like this. And I want to point out that it's very important that you keep the subscripts and the superscripts where they are. So functions, okay, these xi's all have superscripts and the coefficients have subscripts, okay? Because the convention in differential geometry is that there's a conservation of indices. So if you have a subscript and a superscript, they cancel out so that they're really nothing on the right-hand side. And you see on the left-hand side, there are no subscript or superscript, okay? So you have to keep this convention for the conservation of indices to work. Okay, let's take a break for 10 minutes, and we start again at 10:20, no, 11:20. Okay? I just want to say that there will be homework every 2 weeks, just a few problems. You have to get some practice, solving some problems. However, yeah, there are so many auditors, okay? So we cannot grade the homework of auditors, okay? We don't have enough manpower or time. I'll grade some of the problems, and there will be a TA who will grade the other problems, okay? But yeah, we can't grade the homework of auditors, okay? I will give you the problems on the course website, okay? So you have 2 weeks to do every problem set, and there'll probably be 6 or 7 problem sets, and no exams, okay? And if you have any questions, you should feel free to talk to me or to come to my office hours. I'll have some office hours. And, like, unless you come to talk to me, I will never get to know you. So you should try to come to talk to me. Okay, so we just learned that every one form on an open set U can be written as a linear combination of dxi's with coefficients that are functions, okay? And so this allows us to define what it means for one form to be smooth. A one form, omega, which is the sum of AI dxi on U, is smooth, or another word for smooth is C infinity. C infinity means you can differentiate infinitely many times, and all the derivatives are continuous. So a one form is C infinity if all AIs are C infinity functions. All the coefficients are C infinity functions. Okay? And you can do the same thing for K forms, and that's because there is a theorem from multilinear algebra that if alpha 1 to alpha n is a basis for one tensors on V, then to get a basis for the K tensors, you just wedge them together K times. So alpha I1 wedge alpha IK, okay? Now the wedge product is anti-commutative. That means if you switch 2 of them, you get the negative. So you can't have repetitions. If you have repetitions, it will be 0. And so these subscripts all have to be distinct. And you can arrange them in increasing order, okay? Because when you switch 2 of them, it's alternating, right? If you switch 2 of them, it just picks up a minus sign, okay? So it doesn't give you any new basis element. Okay? So when you wedge together k different ones in increasing order, then that's a basis for the k tensors. On V. Okay, now this means that you can write any k tensor as a linear combination of these, okay? And because we know that dx1 to dxn is a basis for the one tensors on the tangent space, you can wedge them together to get a basis for the k tensors. And then you do it at every point, and that gives you, you know, a local expression for the k forms. Okay, so so then we have the theorem that every k form omega on U can be written uniquely as omega is the sum, okay, of coefficients times dxi1 wedge dot 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 wedge dxik, okay, where you sum over all strictly increasing superscripts. And this is too much to write, right? So we'll introduce this notation, a sub I dxi. That's just a notation. Right? So, yeah, so I is this sequence. Okay, such that and once you have this, in the same way, you can define what it means for omega to be C infinity. So definition, a K form is C infinity if all AIs are C infinity functions on U. Okay? And then we have this subnotation. So omega K of U will be all the C infinity K forms on U. Now, differential forms, they are the generalization of functions. And there's a generalization of the derivative. Okay? It's called the exterior derivative. Okay. So I will just state the theorem about the existence and uniqueness of the exterior derivative. Okay. So theorem. There exists a unique R-linear map D that takes a C infinity K form. Well, it just takes, okay, and some differential form to a differential form of one higher degree such that there are three properties. The first one is that D is what's called an antiderivation. And what that means is that if you have the wedge of two form, a K form and an L form, now if it's a derivation, that means it satisfies the Leibniz rule, and that would be this. That would be if it were a derivation, it has the product rule. But an antiderivation means that there's a sign here, -1 to the degree of omega, okay? So that's what an antiderivation is. It satisfies this formula, okay? And the second property is that D composed with D is 0. And the third property is that D on 0 forms is the D that we defined before, is the differential of a function. Okay, well, I haven't explained why the 0 forms is the same as the C infinity function, okay? But I think I'll just leave you to read the book, okay? It's explained in the book why the 0 forms are precisely the C infinity functions. And so D on the 0 forms is the differential that we defined before. And these three properties characterize the exterior derivative uniquely. And it's done in the book, okay? So we don't need that. And now, what does that mean? So now this means that you have a sequence of vector spaces connected by D. Okay, so. Yeah, so thus, there exists a sequence. You start with omega 0, D will take it to omega 1, and D will take it to omega 2 again. And then it will end at omega n because U has dimension n. And after that, it's all 0. And before that, it's 0 because there's no form of negative degree. So we have this sequence. And this is the most important sequence in differential topology. This is called the Rham complex. Okay. A complex is a sequence of vector spaces where d squared is 0. Okay. Now, these are different d's because they have different domains. So I'm going to indicate this one by saying that it's d0, this one is d1, this one is d2. Okay. And then, so since dk composed with the previous one, dk minus 1 is 0, that means the image of dk minus 1, when you apply d to it, it will be 0. So the image of dk minus 1 is the kernel of dk. Is in the kernel of dk. So it's a subspace. And when you have a subspace, then you can take the quotient space, and that's the definition of the de Rham cohomology of U. The de Rham cohomology of U is the kernel of dk. The kth de Rham cohomology is the kernel of dk over the image of the previous one, dk minus 1. Okay? And the kernel is usually denoted by zk and the image by bk. Okay, B stands for boundary and Z stands for cycles. So you might think that, well, if it's cycles, it should be C. Okay? But it's Z because it's German. Yeah, so Z, oh God, I hope this is the correct German word for cycle. Because in the 19th century, you know, Germany was the center of mathematical research. And so all the Americans went to Germany for their PhDs, and then they come back speaking German and with German terminology. Okay. All right, so that's the Rham cohomology. And let's do an example. I have to go to the gym to exercise my arms. Okay, so let's calculate the Rham cohomology of the real line. Okay. The real line has dimension 1, so it has only 0 forms and 1 forms. And the 0 forms are the 0 forms are functions. So this is just all functions, C infinity functions. Now the 1 forms, they are all multiples of dx. Okay, where g is the C infinity function on R. Okay. So let's first calculate Z0. Z0s are the cycles. And so that's going to be all function such that df is 0. df yes, I didn't do this formula, did I? But yeah, df, well, because I have only 3 minutes left, I'm just going to tell you the formula. df is f prime x dx, okay? We can work that out. In general, in higher dimensions, df is df dxi dxi, okay? That's the general formula. It's in the book. Okay, so if this is 0, then that means the derivative is 0. What are the functions with derivative 0? That means f is constant. Okay? So z0 is just all constant. z0 is r. And b0, well, that's the image of the previous one. But that's just 0. Okay? And therefore, this implies that H0 of R is R over 0. The quotient of R over 0 is R. Okay? That's H0 of R. And now let's do H1. So H1, so you have to do Z1. Z1 would be all the gx dx such that b of gx dx equals 0. But this would be a two form. A two form is automatically 0. So this is automatically 0. And so it's actually, Z1 is actually all gx dx. Okay? So it's determined by this function. Therefore, it is the same as all C infinity functions on R. Okay? And then B1, it's the set of all D of a function, df, and df is f prime x dx. So the question is, like, given any g, is it the derivative of some function f? Is every C infinity function the derivative of some other function? Yeah. Well, if G is the derivative of F, what do you call F? F is the antiderivative. It's the indefinite integral. So yes, you just take f of x to be the integral, say from 0 to x of g of u du. Okay. So this says that Z1 is actually contained in B1 because every C infinity function is the derivative of some C infinity function. And so you actually have equality. And so H1 of R is Z1 over B1, and that's going to be C infinity functions over C infinity functions. And so you get 0. Okay? Yeah, so that's the Rham cohomology of R. Okay, yeah, so I will stop here today. And yeah, I hope to get the website working so that, you can read the book. Yeah. All right. Yeah, see you next time. And if you have questions, I am happy to talk to you.